Abstention only works if errors actually fall as coverage drops. Risk coverage curves show that trade-off instead of guessing a reject threshold. This is the kind of pipeline you'll be able to reason through and build, one that maps risk coverage trade-offs and chooses a confidence cut to respect a risk cap. I'm Professor Pi, teaching AI foundations with simple Python. In production, you do not always want a model to answer everything. Some mistakes are costly. Human review can be expensive, but blind automation can be catastrophic. Risk coverage curves give you a clear map of what you trade when you let the system abstain from low-confidence cases. Success looks like fewer critical errors while only shifting a manageable fraction of cases to people. At a high level, the idea is simple. We rank predictions by confidence and track how error rate drops as we accept fewer cases. If risk falls quickly, abstention buys safety with low human load. If risk barely moves, abstention is not helping, and you need better scores or a different model. This visualization turns a vague policy into a defensible choice. For this video, we will build a tiny toy pipeline that makes the trade-off visible. You will get a baseline curve, a calibrated curve, and a rule to pick a confidence cutoff that keeps risk under a cap. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now let's construct the toy baseline so we can see how bad always predicting can be. This snippet constructs a toy classifier outcome so we can see baseline risk without abstention. We explicitly create y-true and confidences as numpy arrays, so every mistake is visible and reusable later. Preds thresholds confidences at 0.5 to emulate an unconditional classifier, and risk averages the resulting Boolean error mask. Keeping coverage fixed at 1.0 shows how little flexibility exists before abstention enters the picture. The printed full coverage and baseline risk values show the uncontrolled starting point we will try to beat. Next, we need to turn that static snapshot into a full trade-off curve so we can see how risk moves as we abstain more. This example calculates risk coverage pairs by sorting predictions from most to least confident. If you want to know how fast risk falls as we defer more, you have to rank by confidence first. Sorted conf and sorted truth keep the arrays aligned, letting errors sorted identify every misprediction at each cutoff. Coverages divides accepted counts by n to show how much work the model still handles. Risks accumulates the Boolean mistakes, so a single vector shows the whole trade-off. The printed half coverage and half risk numbers expose what happens exactly halfway down the curve. With the curve in hand, teams often need a single policy, the highest coverage that stays below a risk cap. Let's compute that decision point. This code finds the most coverage we can keep while meeting a risk target. Stakeholders want a concrete limit, so target risk pins down an acceptable error rate. np.where locates every risk entry below that ceiling, and best IDX picks the most permissive option still inside the guardrail. Chosen cov and chosen risk read directly off the risk coverage curve we already built, so we never recompute metrics. Cutoff pulls the matching sorted conf value, turning the chart point into a simple confidence threshold the system can use. The printed goal risk, goal coverage, and cutoff numbers make the trade-off explicit for anyone approving the policy. Sometimes the scoring itself is imperfect, and a little calibration moves the curve. Let's nudge confidences and see the effect. This snippet perturbs confidences to mimic calibration and measures the new curve. To show that better scoring can actually help, we copy confidences and nudge a couple of indices towards safer values. Those direct tweaks on calibrated confidences are a compact stand-in for real calibration. One true positive moves up, one false positive moves down. np.clip keeps values valid, and cal order resorts so the new ranking propagates. Cal errors and cal risks repeat the cumulative math, letting delta risk quantify improvement at every coverage level. The printed half drop and half risk new values show how much safer the decision becomes at the earlier target. Finally, visualizing and summarizing the change helps build trust with stakeholders. This example renders the risk coverage comparison and summarizes it with area under curve numbers. Seeing the curve matters, so matplotlib plots coverages and risks for both baseline and calibrated traces. ax.plot draws the lines, and ax.scatter drops the chosen chosen risk marker so the chosen policy stays front and center. Axis labels and ax grid give viewers the context they need to judge how fast risk falls as coverage shrinks. plt.show makes the figure visible during demos, while the np.traps calls compute comparable AURC scores for documentation. The printed AURC baseline and AURC calibrated values confirm how much safety we gained overall. A quick wrap. Risk coverage curves show error rate versus the fraction of cases the model still handles. Use them whenever you can route low-confidence decisions to humans or another system. They turn a fuzzy choice into a measurable trade-off. One caveat: if confidences don't track correctness, abstaining won't help until you fix the scoring. Next step: scale and evaluate this pipeline on a larger corpus, and add timing and accuracy checks so you can measure human cost versus error reduction in production. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.